Hello, hello, hello. Good afternoon, everyone. I am going to be going over the current balance lab um, for Physics 30. This ties into very well into Physics Unit B, and is something I often do with one of the labs I often do with my class. It is a question that similar questions, not exactly the same. Similar questions tend to be tested on the diploma exam, and I usually go over this lab or something similar for my class as well. So here is how to analyze and approach the current balance lab. So the current balance lab is fairly simple. For this particular design, we're trying to find the magnetic field strength of the battery below from measured data measured in about this lab. However, it looks like I'm experiencing some technical difficulties, as in that my notebook is not moving and it's currently stuck. Oh, there we go. Okay. It moved a bit. This thing about live streaming is if there's a bug, there's nothing you can do about it because it's live. Oh, I see. Hold on. There we go. All right, now it's working. Okay, I fixed the issue that was plaguing it. So I will be going over the how to analyze current balance lab. If you are from my class from this year, 2023, at this point you should have already completed the lab and handed the lab report. If you have not done so, I am going to live turn off the assignment. And if you have not submitted the lab yet at this point, I will no longer be accepting it. So there we go. But because I'm reading answer key is something I would like you to take a look. So hello, I just got some students of mine who's watching. Welcome. So I will be at this point your lab should already be handed in. So this is just a review for you to get an idea, get some feedback from your lab before I actually I will be marking your lab, but this is a review to see if you got the approach to this lab correctly. So as a lab design, it's very simple. It's a application of the electromagnetic induction. In this case, where the electric field will create a magnetic field, and they're gonna interact with each other. In the lab design, let's keep it simple. I'll do it based on what my class did. This end would be negative, this end would be positive, and the current will be going inside the wire, going through in this direction. Alright, in this direction. Now, of course, the magnetic field is going from north to south. The magnetic field is going this way from north to south. And if you use third hand rule, very easy to determine that the magnetic force on the wire is going to be up. However, for the experiment, this board will be fixed in place. It will be fixed in place, so this board cannot actually move up. So instead, due to Newton's third law, this force will be pushed down instead. Okay. So in this case, okay, what we'll do is the design is you'll put this magnet. This is a magnet on a scale, and of course, the scale measures the quote-unquote force of gravity, but actually the normal force on the object. So this object force will be pushed down by the magnetic force due to Newton's third law, and of course the scale will respond with a normal force. Okay. Now, if you have teared the scale before measurement, then depending on the class, okay, if your teacher or myself may tear it, may have not, it's something you should notice. If you tear the scale before you take the measurements, then the effect of gravity of the scale will be, of the magnet will be cancelled. That's why you tear it. So initially we say the force of gravity for the magnet is equal to 0. We simply scale it, everything already. If not, you do actually have to count for gravity. So it's Fm and Fg, and both of it are balanced by the Fn. So you better know the mass of the scale, of the magnet, in order to do the corresponding calculations. We're going to assume we did do the lab properly. Okay, this of course is a source of systematic error. If you notice, your results are kind of off. But we are going to assume that the magnetic force and the normal force are perfectly balanced out using the fact that F net equal to 0. Okay, in this direction, so Fn and Fm are equal in magnitude. All right. So how do we analyze it? Now, of course, our manipulated variable of independent variable will be what we adjust. We're going to adjust the current flowing through the wire. It's going to be current, and I would normally use. I think our lab would use a variable power box. Okay, a dependent variable, of course, is a reading. Dependent variable. Okay, would be the force reading. In my notes, I think I call it the force of gravity, but if you want to be really technical, it should be the normal force, but I'll just call it the force reading here. So if, of course, you're going to have your current measured in amps, measured in amps, and then you should have your force, which is measured in newtons, measured out, and you will graph it out, and then you will graph it out, which I will draw. It all like so, right? And of course, it's current on the x-axis and force reading on the y-axis. And lines should be a straight. I'm going to erase this one actually because it's not perfectly straight. So I can draw a straight line. There we go. It will be a linear graph. Now the key thing is, what does this linear graph tell about us? Well, remember, this force reading is equal to the magnetic force. Right? It's equal to the magnetic force, which means that it's equal to ILB, the magnetic field, and we're looking for this. If you want technical, perpendicular magnitude, we're looking for the magnitude of that, right? Our x variable is that, it's current, a y variable is a force reading. So if we just write it out, Fm, I'm going to assume everything is magnitude here. And of course, I'm going to match this is y, and I'll match this is x. Right? I should say that. So this will be L, length of the wire, times magnetic field strength. So if we match with mx plus b, we'll notice the slope is equal to magnetic field strength times the length of the wire, and the y-intercept should be 0. Now, if y-intercept is not 0, once again, if y-intercept is not 0, there's a very good chance it's because we didn't tear the scale in the first place. So even when there's no reading there, even there's no current there, there's already a reading that's going to be the gravity of the gravitational force of the magnet. Okay, so make sure you shift everything by that amount. Okay, but the y-intercept should be 0 once again. If it's not 0, most likely you didn't tear, or there's some fluctuation in your scale. Big fluctuation in your scale, very big. But most likely you forgot to tear properly. Okay, so y-intercept should be 0. And then, of course, we can find, therefore, the magnetic field strength we can find is take the slope divided by the length of the wire. Hopefully you did measure the length of the wire for this purpose. All right? Some common source of mistake for this lab, okay, for evaluation, some common sources. I'm not going to go through specific ways you can fix this, but some common sources of evaluation. Okay, number one, of course, forget to tear. That's probably the most common one. Okay, that's a source of, this is a systematic error. Okay, systematic error, forget to tear before the experiment. Once again, the whole reading will be shifted by the mass or the force of, the gravitational force of the magnet. Okay, something else you may forgot to do is you didn't zero the current, the ammeter. Right? In that case, once again, it leads to systematic error. Once again, your x-intercept actually be a little bit shifted, right? Even though when there's there's already some current reading right already in there, right into the beginning, so everything needs to be shifted. Okay. Another thing you might want to control is that the another source of error would be that there is a chance, that the circuit board is actually touching the magnet, which means when you zeroed it, when you teared it, you actually didn't tear the mass of the you didn't tear the mass of the magnet. You tear the mass of the magnet and the circuit board, right? And just a little bit of circuit board. It's held in place, right? Because it's pushing down really hard, which means its whole thing's gonna be shifted. So the whole mass is actually a bit lighter because when the magnet gets pushed away, okay, once it gets away, suddenly the mass of the circuit board no longer in effect. So circuit board may be touching. So these are some sources of systematic errors. Circuit board touching the magnet when starting, like pushing, or maybe touching is better, not the most appropriate. Pushing down, you're too tight. Okay, I know for one of my classes, I intentionally put it down really, really tight. I was wondering if anybody might notice. Okay, pushing down really tight, or at least the data will show so, right? The data is like, the whole graph is slightly lower than I expected, pushing down on this magnet in the beginning. Once again, that will result when we tear. In the beginning, you'll tear too much, basically. But when the magnetic force push the magnet away, suddenly that pushing down force from the circuit board is gone, which means all your tearing, all the forces gets messed up in the beginning. You subtracted too much, basically. These are systematic errors. Some sorts of random error would be the ammeter is not very. The ammeter is I used multimeter in my class. It fluctuates. The power box actually fluctuates a little bit. The current does not stay constant. Right? Systematic errors. The power box doesn't actually maintain. So you may want to think about what some ways to provide a constant current. Right? Maybe you want to use a battery instead. Right? Maintain constant voltage or current. Right? This will be random error. Right? Random error. Similar thing for a scale. We maybe want something more accurate to measure the weight, but I think the digital scale still tend to be really good, so I will not list it here. But the most common random error is the power box cannot maintain a random current. Okay, so you will need to use something else that can maintain a constant voltage, constant current. For example, like a battery or something with a fixed circuit. Okay, using variable power boxes tends to come with that issue. Okay, there are some sorts of mistakes, but these are some examples. Mostly systematics, because those are things that we can reasonably fix. Okay, while some other random errors can also be reduced, such as the power box. All right, and that is the lab for the current balance. Thank you for watching. For those watching live, anybody have any questions? Type in the chat. If there are none, I'll wrap up this live stream about the current balance, and I wish you all have a great afternoon. Bye bye.